Hi everyone! Today I will show a short visual example on how heap sort works. Hopefully this video gives a good visual demonstration on what each function in heap sort does, as well as providing some example Python code. As always, the link to the code is in the description on my GitHub page. First, I start with an unsorted array, and I show the heap representation of the array. Recall that the heap representation is just another way of looking at the array elements, with added coupling between certain elements. Now that the nodes are arranged in a nearly complete binary tree, each node may have a parent or child nodes. The benefit of looking at an array in this manner is that we can rearrange the elements in the heap to have something called the max heap property. More on that later. Creating the heap is simple. It's a mapping of array elements to nodes in a nearly complete binary tree. Here I have the nodes color-coded, as well as the associated array index next to each node. The 0th index maps to the root of the binary tree, and then the binary tree is filled out level by level from left to right. It's important to recognize that the heap is simply a different way of looking at an array. An array can be transformed into a heap representation, and the heap representation can be transformed into an array. If you're familiar with signals and systems, think of it as how the time and frequency domain can be interchanged, and oftentimes one of the views yields powerful analytical tools. Now, let's look at something called the max heap property. The max heap property is when the value at the root node of a heap is greater than the values of the said root node's children. The children of the root node also need to exhibit the max heap property. That is, the subtrees beneath the root node are also max heaps. Let's look at an example. Taking the root node at index 1, the node's value is 5. 5 is greater than the value at the left child's node, 3. 5 is also greater than the value at the right child's node, 2. The children nodes are both leaves, that is, they have no children, so they are considered max heaps. Therefore, the subtree of indices 1, 3, and 4 is considered a max heap. Now let's look at the other side, where we have the root node index at 2. The value at the root node is 6, and is smaller than the value of the left child node, 7. This violates the max heap property. Therefore, the subtrees of indices 2, 5, and 6 is not considered a max heap. Now let's look at a function called max heapify. This function takes in an array, a heap size, and a root index, and corrects a single violation of the max heap property of the subtree starting at the root index. Let's walk through an example with our example array, where the root index is 1 and the heap size is 7. We already know that this is a max heap, so no correction is needed. The first thing the function does is calculate the indices of the root's left and right children nodes. Then it checks two things per child node. Is the child node in the considered heap? And if so, is the value of the child node greater than the value of the root node? In this case, the child is in the considered heap, but the value is less than the value of the root node. The same goes for the right node. Because neither if statement was entered, the larger value index variable is the same as the root index, meaning that the last if statement evaluates to false, and no further action is taken. In this instance, there were no violations of the max heap property of the subtree rooted at index 1, so the function did nothing. Let's look at the same function with the root index of 2. We know that this is not a max heap, so hopefully the function will correct that. Again, we calculate the child node indices. However, now the first if statement evaluates to true. The variable larger value index is updated with the index of the left child node. Now, a comparison of the right child node's value and the larger of the root and left child node's value is done, which in this case is false. However, when we reach the final if statement, the larger value index is not the same as the root index, indicating a violation of the max heap property was found. This violation is corrected by swapping the value at the root node with the value at the larger value index node. In this case, 6 is swapped with 7. Now this swap might cause downstream max heap violations for the subtree rooted at index 5. Therefore, max heapify is called again with a new root index of the swap child node. This recursive function call may continue for each level of the considered heap. In this case, there are no further violations as index 5 is a max heap. Now, let's create a maximum heap for all subtrees of a given array. Fortunately, this is a simple task. Our function buildMaxHeap consists of a simple iteration of the previously discussed maxHeapify function. Here, we start at the bottommost non-leaf node and correct any max heap violations. We can start at the bottommost non-leaf nodes, that is, the floor of the heap size divided by 2, due to the fact that any leaf nodes are guaranteed to be max heaps, as they have no children nodes. This lets us iterate n over 2 times instead of n times. Here, the function starts at index 2, and like we saw, corrects a single violation in the subtree shown. Then, at index equals 1, maxHeapify does nothing, as the subtree has no violations. When index equals 0, we have a violation that is corrected by swapping 1 and 7. However, this causes a violation in the subtree rooted at index 2. That's why our recursive call of maxHeapify is important. Swapping values may cause the downstream tree to no longer be max heaps. Here, the recursive call rectifies this. Now, we're left with a max heap. Finally, we are ready to implement heap sort. Step 1 of heap sort is to take the input array and convert it into a max heap. This we already did with buildMaxHeap. Observe that the maximum value of the array needs to be at index 0. If the maximum value of the array was anywhere else, there would be a violation of the max heap property. Notice that the same cannot be said of the minimum values or anything like the second or third greatest value. These values are not guaranteed to be located at any specific index in our heap. After building the max heap, we iterate on the ending index of our heap. This value is also the size of the considered heap. On the first iteration of the loop, the heap end index is 6. In the loop, the value at index 0 and the last index of the considered heap, 6, are swapped. This places the array's maximum value at the last index. However, this swap probably made it so our heap is no longer a maximum heap. Thus, maxHeapify is called again, this time operating at the root index and with the heap size of 6. This makes it so that the value at index 6, the end of the heap, is not considered when correcting any maximum heap violations. Thus, the value at index 6 is not going to change anymore, and I signify this by graying it out. On the next iteration of the loop, the heap end index is now 5. Because maxHeapify fixed our previous max heap property violation, the maximum value of the considered heap is again at index 0. Again, we swap values, sending the new maximum to the end of the considered heap. And again, we fix any max heap violations. This iteration continues until there are only 2 nodes left in the heap, that is, when heap end index equals 1. After this, almost as if by magic, the array is sorted in ascending order. Each iteration puts the local maximum at the end of the considered heap. Note that this works because the subtrees of the root node at index 0 are always max heaps. Thus, after swapping, there is at most a single violation of the max heap property for the considered heap. In the background, I'll play the algorithm at full speed. Hopefully this video and its audio-visual content have provided some insight on max heaps, heap sort, and the underlying functions behind heap sort. Thank you for watching.